Okay, I'm John, and here's a spoiler for this talk. If you take your thumb and your forefinger, and you look through the little gap you have between them, and you look at me right now, you will see bits of me shaking around behind that gap. But the distance between your fingers will be roughly constant. If you take a mismatched thumb and forefinger and look through that gap, you will have much more difficulty in keeping that distance constant. And that's your live demo. The rest of the talk will formalize that idea. All right, we're going to be talking about hover sensing. If you're here last night, then Ken Hinckley presented a very nice exploration of the design spaces of devices which can recover the configuration of fingers before they make contact with a touchscreen-like device. And I'm going to focus on a very particular application of signal processing to extract more from the physiological sensors that we have. So you have a device like this that's measuring self-capacitance on a 16 by 10 array in this case, and there's an onboard API which is tracking the finger positions. You can see the height above the surface given by the radii of those circles. And here's the concept. If we can group the fingers according to the hands to which they belong, then we can extend the capabilities of the device. So if I do a bimanual zoom gesture, I can have that do a different action than doing a unimanual pinch to zoom gesture. If I have multiple users above a hover touch-enabled tablet, and they are doing, say, photo sorting, and you put your finger across one that I'm holding onto, the system can recognize that I own this photograph and you can't pull it away. So we can distinguish between users if you can do this grouping of fingers to hands. So how are we going to do that? Well, if you have human muscles, and I think most of you probably do, then you have muscle tremor. And tremor is an always present, insuppressible artifact of human motion. Tremor is modulated when you do different things. If you grip harder, if you're intending to do things, your tremor changes. But it's always there. And it's always present as an oscillation at about 6 to 12 hertz. Now, if you consider the maximum range of voluntary movements you can do with your hand, that extends to maybe 4 to 6 hertz. So we have a signal which is essentially independent of your voluntary motions. And the key thing is, if you have body parts which are connected together, then mechanical linkage means that tremor propagates through those joints simultaneously. And tremor is also a neurological phenomenon. It's not a muscle phenomenon. And there are two independent tremor generators in your body which are lateralized. So you can distinguish between the left and right parts because they have different oscillations. So we take a look at somebody holding their fingers steady above one of these hover touch devices. You get a trace like this on the left, which looks like a mess. Now remember, the units there are in micrometers. These are relatively small motions. And if you take a bandpass filter and you split it into the below 4 Hz, the voluntary motions, and the above 4 Hz, the involuntary motions, you get these two paths here. You get a kind of wobbling of the hand, and you get this what looks like a noise ball with a diameter of about 100 micrometers. But that's not electrical noise or measurement noise, it's tremor. If you look at the Fourier spectrum, the magnitude spectrum, you see this nice monotonic decline in the energy as you go up in frequency, except for this peak at 9 to 12 hertz. And you can listen to this possibly. Let's see if you can hear that there. Maybe not. But you can hear that a little bit. You get this kind of wavering sound. And that's a characteristic sound of the hand hovering above. And then to do this gripping of fingers, we borrow a technique from neuroscience used to identify neurons which are firing together. We use phase synchronization, which is highly robust to variations in amplitude and frequencies. And to do that, we use a bandpass filter to select and isolate the tremor frequency. We then use the Hilbert transform to unwind that oscillation and recover the original rotation which is generating that motion, and from that get the phase angle. We can then compute the phase locking value, which is a generalization of correlation to values which wrap around it, minus pi and pi. And then to robustly identify that this is a real synchronization, we use data surrogacy, where we take the data, we compute the synchronization, and then we repeat that with randomly time-shuffled variants. And we can then make sure that we have evidence that this is a real synchronization event. I'll run you through how that works in practice. Here are some traces from a real finger. we have the no synchronized case, so that's 2 fingers from 2 different hands, and the synchronized case, 2 fingers from 1 hand. So first of all, we do the bandpass filtering. You can see there is similarity in the synchronized case, but there is still amplitude variation. We transform to phase space, and we can see that we have very strong correlation between the synchronized fingers, the ones that belong to 1 hand. The synchrogram plots the phase of one against the other. And you can see in the 2-finger case, it's essentially random. We have a scatter plot spread across the entire space. When we have 2 fingers from 1 hand, we get a clustering about the line. And that's what the PLV, the phase locking value, estimates. And then we do that with the time shuffled variance, the surrogates. We fit a distribution and we work out how probable is it that we would have got this if there was no involvement of time, if there wasn't any real synchronization. And you can see in the no-sync case, it's about 0.5 is the probability that lies in that distribution. In the synchronized case, the chance you just saw that by chance is about 10 to the negative 136. Okay, it's unlikely to have occurred by chance. So a very robust measure of the probability of synchronization. So does this work? Of course it does, right? But I tested it anyway. So we took 8 people, had them with one of these devices, holding their fingers in 20-second periods, and repeated that 3 times, putting the hand down in between. We did a bunch of different conditions, including 2 fingers from the same hand, both static and moving in circles, and 2 fingers from different hands. Right, this is the challenging case. If you have 2 different people, their tremor is going to be pretty different anyway. One person with 2 fingers in different parts, that's the challenging case to look at. So we recorded their position, we recorded that at around 120 hertz, we applied the filtering, applied the Hilbert transform, and then we did the surrogate test. And the results are pretty positive. You have a very, very significant difference between the Z-scores you get for hands which are on fingers on the same hand and fingers on the different hand. Interestingly, the effect is more significant in Z, that is the direction perpendicular to the surface of the device, than that parallel to the device. Possibly that's due to differences in the resolution of the device and the ability to resolve the finger position, or possibly due to the biomechanics and that holding your finger above actually just oscillates a little bit more easily. But we start to see a very strong effect there. So this is a very cheap, easy way to extend the gestural capabilities of the device. It's essentially free. You're already filtering that information out. You might as well use it. The computational cost is almost nothing. You could implement this on the firmware of the device. It's a very simple bit of linear filtering. And you get robust grouping. Didn't show the results here, but we can group up to 4 or so fingers. The limitation we face is that you can't get more than 4 fingers above our device. But you can probably do that for larger and larger groups of fingers. Of course, there's caveats. It only works for free air gestures. That's why you've not seen it before, because if you bring your finger into contact with the screen, the mechanical damping will eliminate that oscillation. And there is latency. If you have a 10 hertz signal and you want to detect synchronization, and you've got 2 or 3 cycles, that's 200 to 300 milliseconds you're going to have to wait before you can pronounce that synchronized. And it's applied after finger tracking. So you could do interesting things if you could distinguish the fingers using the tremor before you try to separate out the finger objects themselves. We have some early work on doing that, but that could really extend the capabilities when you have very closely spaced fingers. Thank you.
Andy Wilson, Microsoft. I'm wondering if there's enough time in when the user approaches the touchpad or the touch surface. So I look at this as a really nice idea and really looks really good, but the notion of holding your fingers above the touchpad seems a little difficult on the users, right? Why are they doing this? They might have some other reasons. Ken showed some of those. But then I'm wondering if you can just do this right on approach before you land.
I think that's probably at the edge of the time you would need to do it. So if you have about 5 centimeters of range in these devices, then you might get 200 milliseconds with the fingers in there, but it's probably closer to like 80 or something. So I think it would be quite difficult to detect the synchronization there. So it's probably most appropriate for the case where you're doing the mid-air gesturing. So your hands are dirty, you want to swipe to the next thing, your hands are above there for a little bit longer. But if you have a very fast approach, then I think you have difficulty detecting synchronization.
Hi, John. Very nice talk. So you kind of mentioned at some point that the signal is independent of the sensor noise, but you didn't quite tell us what you do with the sensor noise.
Well, sensor noise is very small compared to the tremor signal. So in the measurements there, we had about 100 micrometer diameter of that noise ball. You're probably talking about 1 or 2 micrometers for the actual noise on the tracking there. So the accuracy of the device is sometimes relatively low because of poor calibration, but the precision of it's pretty high. So we have very, very low measurement noise.
Okay. And it's not a problem that measurement noise is also periodic, probably, or same oscillation?
It's not in the same frequency band,
okay.
so it's higher frequency. I think if you had different sensors, so if you're using optical sensing, then you might have much more of a problem with the tracking there. But with these hardware touch sensors, then you have both high spatial and temporal resolution.
And then maybe a follow-up question, because he said if you had another high-resolution sensor, so have you thought about what other limbs? So the tremor is in all of our limbs, right? What else could we think about using this for?
Well, I certainly think things like if you're doing like connect and you're doing free air gestures, you can do that, and you probably could see that fairly significantly. I'm not sure about other limbs. So doing on the legs, because your feet tend to be in contact with the ground, it's very unlikely you're going to see any effect there. But certainly, if you have a high-resolution sensor which can pick up those variations, then I think you can get pretty useful signals.